Hola mi amigo, bienvenidos. Welcome to this channel. Today we are going to learn about the structural design process. I'm going to show you the guidelines that you should take into consideration once you want to design a structure. So if a client has called you, or you have a school project, or you just want to design a building, there are a few things that you need to take into consideration before you start with the design. And previously we have shown you how to use softwares in this, and now we're going to show you how to do this manually, so that you understand this from the first principles even as you proceed to either use the softwares or to design the structure using handwritten or manual calculations. Of course, the codes come in handy, so you should ensure you have your codes ready. If it is concrete, you should have your British Standard or your Eurocode. If it is steel, the same. For steel we do Eurocode 3, and for loadings we do Eurocode 1 and all those other parameters. So have your code ready, be reading the code, get used to knowing the principles in the code that should be followed during design. So today I'm going to show you the basics of design. Having showed you the structural design process in one of our videos, today I'm going to take you through, once a client has given your project, how do you start decomposing the loads from your slabs to your beams? What are the considerations you should generally be making before you proceed and design the structure and come up with the drawings and go to site to supervise the work? So there are a few things you should ask. For instance, once somebody tells me I have this structure, it is maybe a 5-story structure, one of the basic questions you normally ask is, what is the soil type in that area? Is my structure going to rest on a rock? Is my structure going to rest on red soil or even black cotton soil, whichever that soil in the site? So hope you're going to learn, and in such a case like the one I have given, you should go to site, do a geotechnical investigation, and find these things out before you start carrying out these processes. So I'm going to take you through the structural design guidelines. After I have my structure, here are 3 guidelines that I normally would want to look at before I start designing. First of them is the conditions of the site where you want to build. And for the conditions, you should look at the environmental conditions, because the issues like humidity and the environmental conditions that my structure interact with affect some of the parameters we use in design, including concrete cover. If I'm building, let's say, at the coast where I have a lot of salts in my soils and my underground water, then I need to think about how am I going to treat my steel, and how I'm going to look at all these other parameters. Secondly is the loads that will be acting on my structure. For the loads, I should ask myself, what is the utility of the structure? Is it a residential one? Is it a commercial one? Is it an industrial utility? Or is this a library? Is it a school? Whatever it is, the codes have actually highlighted how you should treat these cases and the loadings you should apply. So you should determine the loads that are acting on your structure basically before you even start designing the structure. And then the design of my structure. How is my structure going to be designed? Which software is going to be more efficient in designing my software, my structure, if I am going to use a software? And which methods am I going to use so that I can come up with a structure that is economically designed and at the same time it is safe? So that is those are the 3 parameters you should look at. Number 1, I've already talked about the site conditions. That is the maximum load bearing capacity of my soil. And for high-rise structures or when you're doing story buildings, it is good that you go to site and you test for bearing capacity of soil. There are very many methods of doing this. You can use plate load test, where you can test the soil in situ, or you can even take the soil to the laboratory and use the shear box test to find out your angle of shearing resistance and your C, that is the cohesion of that soil, so that you can come up with a bearing capacity of the soil. Also the foundation that I want to build on this soil, some of these things you just determine before you start designing. The structures, once you think of designing them, what comes into mind is I'm going to use a raft or a mat because the loads are very high. Or sometimes, depending on the soils, you might want to do piles or other systems like strip footings or pad footings, depending on the soil site conditions and also the loading from your structure. And then there could be any requirements that might be required to improve my soil. If my soil is poor, I need to do maybe geotextiles or some either chemical or mechanical strengthening of the soil, so that it is able to bear the load from my structure. And then also the water table is very, very important whenever I'm building my structure, because sometimes we overlook issues of buoyancy, the effect of the water table on bearing capacity of our soil. And sometimes when the soils are poor, the water table, if it's very high, like in black cotton soils, you're going to have alternate expansion and contraction of soil, which are going to affect your soil and therefore have adverse effects on your building. So these are the site conditions you should consider. Secondly is the load, whether the way I'm going to distribute my loads to the foundation. And we stated that you need to determine the loads that are coming for from your structure. If there are heavy loads, there are some systems you should incorporate. If they are not, the structure is not that heavy, there are also some systems you can incorporate. So I have gone through something here about load bearing and framed structures. Once you have determined the load from your structure, you need to decide the way of transmission of loads from your roofs to your foundation. Sometimes we do load bearing structures and sometimes we do framed structures, and I'm going to explain the difference between these two structures, so that once you start designing, you are able to pick one, and actually it is going to be efficient, because once you've picked something and then you know from your preliminary design that it can work, and from the conditions of the soil, then go ahead and design it. It will even save you time. So for framed structure, we normally use a framework or a skeleton of just beams and columns and slabs to carry the loads to the foundation. In this system, we don't use load bearing walls. We could be having walls in our structure, but these walls are not acting as structural elements that will help us distribute the loads to the foundation. These walls could be maybe act as partition walls or walls demarcating boundaries, things like retaining walls and all that. But in terms of distribution of our loads from the roofs to the structure, these walls do not play any part. In load bearing, the walls are designed in such a way that when the loads come from the roof, they are able to be distributed to the foundation through the walls themselves. And once they get to the foundation, they use some foundation systems called strip footings. Therefore, load bearing structures use walls to distribute the load to the foundation, and framed structures use a system of a frame-like structure which encompasses the foundation, the column, the beams and the slabs to distribute the loads to the foundation. And sometimes in framed structures we normally have things like shear walls. For instance, if you have a high-rise building and you have lift scores and some shear walls in certain locations, it is not going to make it a load bearing because we have some shear walls. It is still a framed structure, but due to bracing systems, I will discuss what are bracing systems later, but due to bracing systems as they are required in a high-rise structure to distribute lateral loads to the foundation, therefore we have them in our structure. Therefore framed structures can have shear walls, and also have columns and beams and slabs as their load distribution mechanism. Therefore, here are a few main differences. Number one, for framed structure, it has beams, columns and slabs, as I have already mentioned, but in load bearing structures, the loads are borne by walls, where the walls transmit the loads to the ground. And these structures, sometimes they have columns. It does not mean these columns do not transmit any load, but the main load transmission system for this is for the walls. And actually, in some cases, engineers combine framed structures and load bearing structures, where they build foundation systems for columns, for instance pad footings, and they also do strip footings for the walls. So sometimes engineers can design and combine this so that they can come up with an economical structure. But basically, a framed structure just has beams, columns and slabs, and load bearing structure has also walls as load bearing systems. In frame structures, the slab, the vertical load transfer path, as I have already mentioned, is from the slabs, which are decomposed to the beams, and then from the beams to the columns or shear walls. And actually shear walls behave as columns, but they are just slender columns in one direction. So these bear the load to the footings and then to the soil. But in load bearing structures, the load is from the slabs, and it could be directly to the walls or to beams and then to the walls, and then the walls transmit the loads to the footing. For framed structure, we can construct multi-story buildings of any heights. Actually, right now we have surpassed 1 kilometer high structures. How tall is the Burj Khalifa? Go and find out. And then we have structures which are already coming up, which are even taller than the Burj Khalifa. Now, when you have such structures, you cannot have them as load bearing, but those structures are normally framed structures because the loads are massive and the heights are also very high. So for framed structures, we can go to very high limits. And then for load bearing structures, the codes, depending on where you are, the wind speeds, and whether you have earthquakes in the area, the soil properties and all these parameters, they have a limit to which you can design the structures. Some codes talk about 6 floors. You can only do load bearing to 6 floors, but currently we have structures even up to 14 or 15 stories, which have been purely designed as load bearing walls. And I will give you a quick story. At one time I was working with the county government of the city where I live, and then structures were coming down in a certain area, and we wanted to find out what was the cause. So we went studying the properties of the buildings in that area, and we came across one building which was constructed in the 1980s, and it was purely made of stone and mortar. There were no columns, there were no beams. It was stone and mortar and slabs. And one engineer looked at it and said, this one has to come down because we cannot be sure of anything. But upon carrying out checks and finding out the structural aptitude of the structure, whether it is safe for occupation, we found out that the structure is very safe. It had no cracks or signs of failure, and at last we recommended that the structure is safe and the people continue occupying it. So some of these things are possible if only you sit down and design them properly. For framed structures, they are more rigid and more resistant to lateral loadings, including wind and earthquake. And actually we designed them for that, where we make structures braced, and then we include shear walls or any other systems that can distribute lateral loads to the foundation. But for load bearing structures, they are normally very weak when it comes to earthquakes and seismic loading and even wind loading, and these can bring the structure down. You can try these. You can simulate a wall. Let's say you simulate 15 meters high wall made of masonry without beams. You can simulate these in one of the best softwares we have for simulation is Abacus. You can simulate that, and then you do your basic wind speeds. You can do wind speeds of 45 meters per second, and then you find out how the structure will behave. You will realize that for load bearing it can even come down, or the stresses will be very high because walls are not good distributors of loads to the foundation. In frame structures, the walls can be thinner. You can make walls as thin as 100 millimeters. You can make walls out of anything, including timber or gypsum, or you can use steel, masonry steel, or anything you want to make walls with, because walls here are basically partitioning of one room to the other. But in load bearing walls, there is a minimum breadth to which your walls can extend, after which you can now start designing. And for instance, here in Kenya we use 200 millimeters walls and more as load bearing walls. And next is in frame structures. Normally we construct the skeleton first, where you do the columns and then beams and then slabs, and then you do the walls later. But in load bearing systems, you have to do the walls from the foundation up. You cannot cast a slab and then you do the walls later. No, you have to start with the walls and then you proceed upwards. Frame structures is the most used form of construction, more so for high-rise buildings, and load bearing structures are rarely used unless we are working with bungalows or mansionates, or structures really whose load is not that very heavy. That is why this load bearing system is not a very common system that is widely used. And excavation for the type of construction of a framed building is actually normally less, and for load bearing excavation is more, because you have to excavate for strip footings where your walls are going to lay. But here you can just do your pad footings, you concrete and fix your reinforcement, and you start construction. Some excavation in frame structures is not so much as it is in load bearing structures. Framed structures are less material intensive, and they consume actually more cement and steel. But for load bearing structures, they are more material intensive, hence the dead load is actually more, because if you have thicker walls on all your stories, it means you're going to have a very heavy structure. But if you do a framed structure, then you're going to have walls made, you are going to even have curtain walls, which is actually a modern form of construction where we use glass to as parts of our walls, and glass is lighter than masonry, so you see it is going to be light, and that thus it allows us go to as high stories as we would wish. Room dimensions can also be altered in framed structures, but in load bearing you cannot. It basically wants you to do your walls at the same position, at the same location from down upwards. Though you can shift the walls, but that would require introduction of beams and some calculations as the structural engineer. But in framed structures, you can design a structure with ground floor walls are in different locations, first floor walls are in different locations, second, and all that. Cantilever elements are also easily provided in these systems because they are fixed systems, and inclusion of cantilever elements in load bearing structures is normally fixed to some short spans, because they are not as rigid as they are in framed structures. The stiffness of load bearing structures is not that much as compared to framed. Therefore, these allows you introduce cantilevers up to certain very high lengths as compared to load bearing. In framed, large span areas are also possible, and there are no limitations of span. What is required is just to follow the rules of construction and design. You do what is required from your code, and you're going to be home and dry. But in load bearing structures, you cannot do large spans of your rooms, because there are limitations of the loadings and the moments that your walls can carry. Therefore, I have explained about the difference between framed structures and load bearing structures. Next, we're going to look at a structure's loads. What are these loads that we are talking about? A structure has high load, a structure has low loads. One of the structures is dead loads. Dead loads, this is a term we used to use in the British standard, but when you come to the Eurocode, we normally use permanent actions. Dead loads are those permanent loads that you're going to have in your structure that come as a result of self weight of the building or any fitting or fixture that is stationary in that structure. Therefore, dead loads exist in all buildings, because the weight of that masonry, the weight of that finish, if you're doing your tiling, if you're doing your plaster, if you're doing the elements themselves, the dead weight of the beams, the slabs and all that. So dead loads are permanent loads that you are not going to alter from the structure, and every structure has dead loads. For live loads, these are loads that a structure is subjected to while either under construction or use. Actually, sometimes we have some loads that are in a structure during construction which are not there in use. For instance, sometimes you do your scaffolding or your support systems on your structure, and this is transmitted to the foundation. Therefore, live loads are just these loads, movable loads that are subjected to a structure, which can be either dynamic or static. By dynamic, I mean loads like earthquakes, wind. Or static are these loads that once they have been placed, they are not easily moved. For instance, if you do like if you have a bedroom, it must have a bed. So that bed is a live load that is static in nature, because you can carry the bed and move it from the room, but in most cases it will be resting on that room, but it is a live load because you can remove it and bring it back. And the codes have given guidelines on how these loads are combined. Next is wind load. Wind load is a type of live load that comes as a result of the horizontal action of wind in an area due to the building's surface area. Because the building has a surface area and wind is running horizontally, therefore the wind has a load that it impacts on our building, and wind speeds are normally calculated depending on the zone where we are, and actually every zone has its own basic wind speeds, so you should not use different wind speeds for a different zone. Just find out where you are, go to the meteorological department, get your wind speeds so that they help you when designing structures for wind. Last but not least, because loads are many, the loads that you can have in your structure is earthquake and seismic loads. Earthquake and seismic loads, these are loads that come on our structures as a result of vibrations of the earth's crust. That is due to the earthquakes that happen on the earth. These ones, sometimes if the magnitude of the earthquake is very high, they bring the building down. Therefore, that is why when you're doing a structure, you're required to factor them out as stipulated in the code. Of course, there are structures where it is not really necessary to do. If you're doing a bungalow or a mansionette, you're not required. Well, sometimes if you are in certain locations, it's not a must to carry out earthquake and seismic design. So these loads, sometimes you just assume them, just the same way you assume wind loads if the structure is like let's say 4 stories and below, sometimes we assume and we do not carry out wind and earthquake design. But for dead and live loads, this one you cannot run away from, because all structures are subjected to this type of loads. Having talked about loads, these are not the only loads our structures withstand. Sometimes we have snow, sometimes we have vibrations. There are very many types of loads depending on what you're designing, where you are, and the parameters you want to take into consideration. So these are just the basic loads that we use when we design a structure. Now, having determined all these, the loads you're going to use, you've determined your structural system, whether it's load bearing or framed, you found out your bearing capacity and your conditions of the soil and the environmental humidity and all other environmental conditions. Now, this is the process that we normally use when we designing. Once you get your drawing from an architect, this drawing has grid lines. Grid lines come in handy because they help us identify elements positions easily. So if the architect's grid lines are specific and they can fit your work, you can adopt them and proceed with them. But in most cases, most engineers would prefer to do their own grid lines, where they identify their own and they use them in the analysis. And after identification of grid lines and coming up with positions of elements, the next thing an engineer does is do preliminary member sizing and draw a column beam layout. In one of our videos, we have actually taken you through the structural design process, and we have mentioned a way you just design your members preliminarily depending on the structure height, the loads you have, and the construction procedures and materials and all these considerations. So these, you size them and you draw these layouts, beam and column layout, so that they help you now determine the actual member sizes and the actual specifications you're going to use in your construction. After determination of this, you should also use your experience and a few checks here and there that enables you do the sizes of beams, the sizes of the columns, sizes of foundations and slabs and all that. And these ones, sometimes if you're a young engineer who has not been experienced in the field, carrying out design, a preliminary design becomes a challenge, because you don't know the depth of the beam I'm going to use for such a span. So here you're supposed to have some background information on which depth actually works for certain spans and which depth works for certain spans, and which construction methodology goes hand in hand with whatever I'm going to do here, and is it what is going to be used on site. For instance, for flats, for flats, apartments and mansionettes and maybe bungalows, we do beams that are normally 200 millimeters wide. And when you read the British code, it states that for structural beams, the minimum breadth should be 200 millimeters. So these are the things you should have in mind as you do your preliminary sizing of your members. Next is to carry out now the load takedowns. After you have carefully preliminary sized your members, now start calculating the load takedowns from the roof. We actually start taking our loads from the roof to the foundation. But in this study today, I'm going to show you how we will take loads from our slabs to our beams. So column load takedowns are very important, because they are the ones that give you the loads that you use to obtain your moments and then your forces that you actually design for. After doing column load takedowns, next is analyzing and designing of the member. Now after you have the load that is acting on the member, you have the torsional, the shear, the bending moments, and you can even draw those diagrams. Next you proceed is to design the member. Now designing the member is giving the exact specifications that are sufficient for the utility of the said structure. If the utility changes, the members could be either changed to be bigger or smaller depending on the change, or it could even fail, because different utilities have different load considerations. And after designing, now you also carry out some checks. If it is a beam, you need to do deflection check, find out whether the depth I've provided and the reinforcement are sufficient to counter deflection in my member. And sometimes that member that you had preliminary designed fails. So here is where you come, you change the depth, and then you repeat the process again, you try designing till it accepts. Sometimes also the member you have provided, it is failing maybe in shear, and instead of increasing the size, you can decide to provide shear reinforcement to counter that shear. So here is where you provide the specifications of the member, and then you carry out the necessary checks and correct any failing sections or elements. And then lastly, you detail the elements in a suitable software, and after that you produce working drawings or approval drawings that are normally taken to local authorities for approval, and then you proceed to site. Now, one of the problems we do is we design and we fail to go to site to supervise the works going on site. This becomes a problem because sometimes the developer or the architect or the skilled or unskilled manpower decide to change one or two things of the things you have specified, and when they change this, they still use what you had specified. So they might end up making a mistake and committing a felony that can lead to coming down of the structure and so on and so forth. So the developer and the architect and the engineer and the quantity survey, all these people are supposed to be involved in the project from inception to completion, so that everybody takes responsibility of their duty, the duty they are given on site. So you should ensure all the work that you have designed and detailed, you get the opportunity to supervise it. That provision should be made by the developer and all the teams involved in construction, so that you ensure the structure is built as designed. And if there are any changes made on site, then as the engineer you can go back, design, or advise otherwise. Having said that, I hope that was helpful. Now you know, when I have a client, I have a structure, I've talked to the developer, now I want to design the structure, what do I do? What things should I factor? And now today, from just general knowledge, I'm going to take you how you are going to do your load takedowns for beams. Remember, this is the introductory class. We will have another class for load takedowns for columns and footings and all that, but today we just do beams. Slabs are very simple. Towards the end I'll show you how to do load takedowns for your slabs, but for beams, here is how to do that. I mentioned about doing grid lines from your architectural drawings, or some drawings are not normally generated by architects. If you're designing a bridge, sometimes a bridge is purely designed by an engineer. There are bridges where architects are not involved. So if the bridge has been drawn by you as the engineer, then you should identify grid lines that are going to help you place your critical elements. So use these grid lines, identify them. You can observe I have already I have this building right here, and then I have the grid lines stated. You see, these are, I'm using 200mm thick walls, and then these are the spacing between the walls, but my grid lines are at the center of the beams, the walls, and the columns. You see, let me increase this so that you can observe where they're passing, so you can see where my grid lines are passing. And then identify all the grid lines in both directions. This is the x along the x direction and along the y direction, and also come up with dimensions of any other important features you want to note in your structure. And this is after doing preliminary design. That is when you have identified how wide your beam should be, what should be the size of your columns and all that. And actually this preliminary design does not mean it is going to end up as the actual design, because if the member will fail, I might increase the section, and therefore I'm going to increase it after I have designed it. So after doing the grid lines, size your beams, columns and slabs by doing preliminary member sizing. And one of the hints that is going to help you when you use the British standard, which is code 8110, you can use the table 3.9 to size a few members, and I believe you have the code. If you don't have it, just drop a comment in the comment section and I will send one to you. Draw your beam layout and label all the elements sized and drawn. You can see they have been labeled. I have my column C1 to C15, and then my beams are labeled, but it is very small, so I'm not able to see. And but hope you can see my beams are labeled, the sizes, the depth, the breadth, depth, and the beam number. And after doing the labeling, you distribute your loading to the beams using a suitable method. You can use the yield line analysis, you can use the trapezium area method, you can use the coefficient method, or any other approved method from your code. But the commonly used is the trapezium method for regular shaped slabs, that is square and rectangular slabs, or the coefficient method as stated in the British code that we have stated above. So analyze and design the beam manually using a suitable design software. So what we're going to do is we're going to distribute our loads to the beams, and then once we distribute our loads to the beams, we are going to pick one of the beams and design it using Procon, which is design software. We will also design it manually so that we can compare the result and find out whether our software is over designing or under designing, and the things that it's taking under consideration. So after figuring this out, I have also stated a few notes here on how you should size your beam elements. The first thing you should determine is your beam depth, and for beam depth a hint is that you should use the effective depth of the beam in comparison with the span. So we normally call it depth span ratio. So using these stated clauses in British standard, you can study them, and then they'll help you determine how to get your effective depth, and then how to determine for what spans I'm going to use which depth. Sometimes, though this is a disclaimer, the architect or the developer wants a certain size of the beam spanning for longer sections. So this and when you design it as a reinforced concrete beam, it is going to fail. So this takes you as the engineer to think of what to do so that that beam can be designed as required. Sometimes you're required to do composite sections where you can do a steel section and then you encase it in concrete, or sometimes you decide you forced to do things like pre-cambering of your beams, which has been talked about in the Eurocode. I saw it in the Eurocode 2. Or you can even do pre-stressing of your beams, where you stress your reinforcement before you do your casting. Or sometimes you also do post-tensioning of your tendons so that you can make the beam stronger. So everything is possible if you sit down and do the math behind it and prove from the math that either it's possible or not, or if it's possible, these are its specifications. So let the effective depth not limit us in providing certain depths. When it is really necessary, you can also go ahead and even increase reinforcement, but provide a section that is not as deep as required by this, but this requires design. So you should design and not just provide. The other thing is also determination of the beam width. We have talked about what is recommended in the code, And in most cases for basic buildings we use 200mm beams because they are resting on our walls. So we want, after applying finishes which include plastering or cladding with something, then you cannot be able to identify that this is a beam and this is a wall starting from here. So for this beam width, it's very important, and actually the code requires that the ratio of the depth to the width to be between 1.5 to 1.3. so once you increase the width, sometimes it forces you to also increase the depth. Yeah, sorry. The next thing, after sizing your beams and columns, and you've placed them there, for columns I'll show you how to size them when we do load takedowns in columns. Now determine the load distribution from the slabs to the beams using the trapezium area method. So this is the structure I showed you earlier. This is a typical floor of a flat. It's here, and you can see the dimensions are provided here. It's 4 meters 444, and then here it is 1.3, 3.05, 3.85 and 1.15. so we proceed. Once you get there, the next thing is now you do the trapezium area method. It is very simple. Let me increase this so that you can see. I'm hoping it's clear. What you do, you come to this orthogonal junction, which is an edge, and then you draw a line that divides these into two equal angles, which are 45 because this is 90. After doing 45, you do 45 for all corners, and then you join them at the center to form a series of triangles and trapeziums. You can do this manually. Once you do that, then you determine the actual individual dimensions of all lines, including this one you have, the ones that are going to help you get the area of your shape. So this one had slabs which were rectangular, but they were almost square. That is why you're seeing they are almost meeting at the center. They're giving us 150mm spacing to form these trapeziums and these triangles. So once you do this, this trapezium is going to load this beam. This trapezium is also going to load this beam. And whatever I'm explaining here is for two-way spanning slabs. Just a minute, I'm going to explain to you what are one-way and two-way spanning slabs. Let me minimize this. Here they are. For two-way spanning slabs, a ratio of the longer dimension to the shorter dimension is less than 2. That is when we do the 45 degrees thing, and then for this is a perfect square, therefore all these beams will be loaded by triangles. But this one being a rectangular, we have a trapezium here loading this beam, this triangle loading this trapezium loading this, and this loading that. So you have the dimensions, and then you can determine the area, and then you'll determine the concrete volume, and this will give you the loading that will go to that beam. The same area is what you're going to use for your live loads and so on. For one-way spanning slabs, you actually divide them at the center. You take the mid span, you snap the mid span of the short span, and then you also snap the center of the short span, and then you do the center. So half of this is going to load this beam, half of this is going to load this. Disclaimer is that part of the loading of this slab goes to this beam if there is a beam here, because once you do 45, most of the loading will go to this and most of this loading will go to that, but you will have a very small area going to there, which will form a very small triangle going to this beam. This area is normally avoided because it is negligible, such that once you include it, the results are not going to adversely affect your structure that much. Therefore, that is why we design them as one-way spanning. So hope you have understood. And for one-way spanning, one of the dimensions, which is Ly, is longer than the shorter dimension, and once you do the ratio, it is more than 2 once you do the Ly over Lx or Lx over Ly, and the ratio is more than 2, therefore that is designed as a one-way spanning slab. So hope you have understood that. And I was explaining this. Now once you get this trapezium, because these are two-way spanning, this trapezium will load this beam, but you remember you have another load from this side. This one, when you look at the LY and the LX, they are actually one-way spanning beam slabs. So half of this load will come to this beam and then half will go to the outer beam. I know you're asking yourself question. Now the outer beam has no support because the beams look like they are cantilevers. How come I'm loading the outer beam and then I'm not they are not supported anywhere? Now these are structural systems where you should actually analyze them carefully as the engineer, because once this load gets to this beam is not just lying on air, it is being supported by a certain beam here and another beam here. Therefore it will distribute half of its load here and half of its load here as point loads. Therefore you have as point load here and half as a point load here. Option number 2, you should do there are complex lines that you can draw using yield lines, and those ones are going to give you the aerial loading this will carry and the aerial loading this will carry without point loads. But the most basic for you to understand that will help you is determine this load, distribute it to this beam, decompose it, and then get the actual load, divide part of it here and part of it to the other side. So you realize that this beam will have loading from this side and this side. So to get the aerial slab loading of this, you add this area and this area to get the total area loading that will come here. When you consider this, you have this triangle, the loading will come here, and you have this triangle, the loading will come here. And sometimes, like in this case, we have partition walls. These I believe are 100mm thick walls. These loadings you should distribute them as they are. For instance, I have part of this coming here, and then part of this is also coming there, and then there is like a small fraction going here. So some of these things are negligible. For instance, this part that is on this triangle is so small that its impact is going to be negligible. So you should also consider these things when you're doing your designs. After doing that, I have managed to come up with this to show you how the loads will come. So this color, forgive me, I'm colorblind, I don't know, maybe I would call this blue, or gray could be the best option. So this gray is loading this beam, and that is why I have decided to put a different color on it. And also you have this color, I don't know which color is this, pink. Oh wow. So this is also loading these beams and these beams, and then it is the same case also here. You have this area and this area of this trapezium loading this and all that up to here. Now when you get to here, you have a staircase. In a staircase it's a bit different. Of course, half of it depends with this support system of the stair. Half of it there is a way you will distribute the loads to this beam and half of the loads to this beam. So if you want to do manual design, what you do, pick two critical beams, and it depends with also the size of your structure, but for my structure here I could pick two critical beams and design and analyze them and use that to detail and construct other beams. So here is the loading: beam along grid B, beam along grid 3, beam along grid 2, B3 and 2. So let's look at B. Where is B? Wow, these grid lines are not we have 3 and 2. You can see 2 is here, 3 is here, and B, I believe B is the second one because this was A, this is B, B is also here. And you can observe that these and these are similar beams, and because of the staircase, I have said I'm going to explain later how to do the distribution. I'm going to use this beam here as my grade B. Therefore, those are the 3 beams I'm going to determine their loading. So step 1 is determine the area of slab elements that are supported by beams. I've already explained that. Find out one-way spanning and two-way spanning and distribute the areas to the beams. Secondly, after doing that, is consider necessary design parameters that I'm going to use in my design. One of them is the slab depth. This is also governed by my spans. The beam dimension, remember I had done my preliminary design and detailing, and this is my preliminary details. Depth of my finishes, if I'm going to do screed, styling, I've determined they're going to be 40 millimeters thick. And then the utility of my structure, I started by stating this from the beginning, it is a residential structure. And then column dimensions are 300 by 300 millimeters. The structure is a frame structure, therefore I'm not having my walls are not load bearing, and it is not braced. Later on I'll explain what a braced structures in a different video, but braced structures work well in lateral loading. And then I have movable partitions. If there are any in my structure, I'm going to do 1 kilonewton per meter squared. This is just an assumption I have made from my experience in the field and all that I've carried out. Sometimes you have partitions that you can move, maybe they're made of gypsum or aluminium, and the loading can come to something thereabout. The density of my concrete is 25, but actually, you know, density of concrete is 24, but I'm having 25 because this concrete has reinforcement inside, because it is reinforced concrete. So I'm adding this 1 kilonewton per meter cubic to cater for the reinforcement that is in my concrete. And then for mass concrete without reinforcement, it is 24. The density of my masonry is also 20, and then the floor to floor height is 3 meters. These are important parameters that you should determine before you start carrying out your design. Step 3 is determining the plan areas of the slab panels that are supported by the beam sections and summing all of them up if their loading is uniform. Because in cases like let's say this beam, this could be a balcony where you want to load a live load of 3 kilonewtons per meter squared, and these are residential utility. Maybe it's a bedroom where you want to load 1.5. So you see this is double than this, so you should do all those considerations, and if it is the same, just sum them up and proceed. And then for which beam is this? I believe this is beam B, if I'm not wrong. This one, the one that we said we are going to design. We will do one, and then you can take it as an exercise to do the others. So we're designing, I believe it's this beam. Yeah, for section 1, this beam has 4 sections. For section 1, you determine the aerial loading that is going to that section. So you see this is a half multiplied by that, and then that is 2. I believe this was a triangles, section 1. Let's go back. I think it's this one, or it could be the other way around. This is a 0.65 meters. Let's see that. No, it's not there. That is section 4 that we have looked at, you see. And then that was 1.3 and half, and I multiplied by 2 because they are 2. So you should find this area. This is section 4. This beam has 1, 2, 3, 4 sections. So section 4, I have found out the area of this triangle and then multiplied it by 2 because they are all of them equal. Both of them are loading this beam. And I mentioned that this could be one way, but these areas are very negligible, as you're going to observe. But remember, I also have this beam. Therefore, once you're designing this, also ensure you get this load, you feed it here as a point load, so that it gives you maximum moments for design of this beam. Having done this section, another section is this with 1.525, and another section has 1.825. So another section has 1.5 25, and then another section had 1.825. so I believe this is supposed to be 1.825, but this error is small. It's an error of just a few millimeters, therefore I'm just going to leave it like that. It's an error of 100 millimeters only, and actually it is increasing the area, but if you want to be accurate, you should increase this to 8. Though for purposes of this class, because I've continued the rest of the calculations from these figures, we're going to proceed using this. For section 1, I have also determined the areas, and I had, as I explained, the areas are very small for this section here. I have determined my triangles and then found the areas and loaded them at this beam. Having loaded all these with all these UDLs, UDL is a uniformly distributed loads, I have also determined the point load at section 1 and the point load at section 4. Remember, I explained that all this loading will go to this beam and then it will be distributed to this point as a point load. Also, half of these will come here and half of these will come here. All of them will be summed here and they will be acting on this beam as a point load. The same scenario happening here. So I have determined all that. You can note these figures and try calculating them on your own. So I have done for section 4 and for section 1. Having all these loads, these are areas, my aerial areas of the slab that are loading my beams. The fourth step is to determine the actual dead and live loads for all of these sections, so that I can incorporate them into the beams. So for section 1, I found an area of 0.66. I told you it is going to be negligible. This is so small, but let's try and work with it. We see what will happen. So for my dead loads, I have the self weight of the slab, where you take the density multiplied by the area multiplied by the depth. Area and depth give you the volume multiplied by density, and volume multiplied by density gives you the mass in kilonewtons. I have also determined the self weight of the beam at this section. My beam was 200 millimeters by 450, and this is in meters, and I've done, this is the length of the beam for this section, and this is the density of my concrete, and there is my loading. And then I have finishes and screeds on my slab, which amount to 0.04, that is 40 millimeters thick. Then multiplied by the area and the density, I'm going to achieve that. Also, for movable partitions, I've decided that section might be having some movable partition, and I have determined that. So I have added all these loadings to come up with 6.385 kilonewtons. After determining this, I divide by the total length of my beam so that I can get loading per meter, and I have 5.55 kilonewtons per meter. For variable actions, which are live loads, you can either use British Standard Code 6399 table 5, or you can use the Eurocode 1 table 6.1 and 6.2 to help you determine your variable action depending on your structure utility, which is residential in this case. So I picked a value of 2, though from my experience I know it could be even 1.5, but I picked 2. Actually, they give the values in ranges, so you cannot just pick one. You can decide whether to pick the lower or the higher, or anything there in between. So I picked 2 multiplied by the area. I have that loading per on my beam. So when I take that loading and I divide it by the total length of the beam, I'm going to get 1.14 kilonewtons per meter. After doing this, I combine my actions. This is a combination of the loadings, and for British Standard we use safety factors of 1.4 and 1.6, and for Eurocode we use safety factors of 1.35 and 1.5. 1.4 is for dead loads, 1.6 is for live loads, and when it comes to the Eurocode, 1.35 is for permanent actions and 1.5 is for variable actions. Therefore you sum them up under SLS, you get that, and under ULS you get all that. For SLS is under serviceability limit state, where you assume that you do not have any factors of safety. That is why I have used 1. But once you include factors of safety, then it becomes ultimate limit state design, and that is how I have summed them up. And you can observe, if you do not know the difference between Eurocode and British Standard, you can observe that the Eurocode is giving me a ULS value of 9.8, and the British Standard is giving me 9.2, and SLS is giving me 6.69. So there is a slight difference, but the values are not that far apart. Therefore, once somebody designs with the British Standard or the Eurocode, their values are supposed to be more or less the same. So having done the first section, the second section is here. This is the area. I have already explained all this except masonry. You observed that some sections had some masonry walls, like this one, right? So I have determined the loading of my masonry of that section, and then I have determined using 20 as the unit weight of masonry, and then 2.4 and using 20 as the unit weight, I assumed they are 150 millimeter thick walls. And actually, I think this is not the masonry that is lying on that slab. This is the masonry that is supposed to be on top of that beam, because section 2, if this was section 2, then we have a wall here. Therefore, that is the weight of masonry that I'm calculating here, so that I can get the total loading it's going to have on the beam. And in most cases, we forget to include this masonry. Sorry, this beam does not have any these internal partition loads on this slab. So this masonry that will lie on top of that beam, I have determined it. Its length is where was that? That was section 2. Yeah. Its length is 3.85 meters. That is the total length of that section of the beam, and 2.4 is the height. I assumed I have a height of 2.4, and if I do a beam of 450 millimeters deep, then I'm going to have 2.85 millimeters high section, and I had assumed 3 meters, so this is not right. I'm supposed to have 2.55 because my floor to floor height was 3 meters. So I'm supposed to take 3 meters, subtract the depth of the beam, which is 450 millimeters, to achieve this. But we are going to proceed with our 2.4 since 2.85 is still an acceptable floor to floor height, though you should do it accurately the way it's supposed to be done. It's just changing this and then it will alter your values here. So I summed all these loadings and then did the same from the British Standard and the Eurocode, and found out the variable actions, summed them up on SLS and ULS, and these are the values I got. And then I did for section 3. I have already explained everything. Sorry for that. I did for section 3. I have already explained how I got including the masonry. Remember that beam has some masonry wall on top of it, so I loaded it, and then I found these for the dead load. I found this for my live loads. Yes, and then I summed them up on SLS and ULS and found that. Lastly is section 4, which was also some sort of cantilever. And then I determined this loading to act on it as a ULS, as not as a UDL. And then I summed them up and found these loadings for my beam. Having done that, remember I had some point loads. I also determined the point loads because of the weight of the slab, the beams and finishes and skillets, and found these, and the live loads going to that beam is as indicated here. And I combined my actions for the beam. I found them as highlighted here. And the other section, which is section 4, I did the same as above and came up with these values. And at the end, you can see I have my 16. Now I decided to use the British standard. I have my 16.35 kilonewtons point load here. I have my 38.95, which is here under the British standard. You realize that I have just loaded the whole beam there. Let me explain what has happened using the drawing. This drawing, when you look at it, this was 4 meters and this was 4 meters. So if I distribute half of this area to this point and half of this to this point, it means I'm going to distribute 4 meters because this is 2 and 2. That is why I just determined the total loading and the total loading of the beam, and all of them I fed them here because it is half and half, they make full. So that is how I was able to come up with this sketch. Yes, and you can see I have my loadings, dead loads and live loads, dead loads, live loads. I've decided to place them like this because we are now going to design this beam. Now as an exercise, remember this was beam D, the one we have done. This is beam D. This does not have grid lines. Let me go to a drawing of the grid lines so that we can, yeah, right here. So using beam, we have already done load takedowns for beam grid D. So take any other beam and do the load takedowns. Let me highlight the one with dimensions so that you can see it clearly and do it manually. You can do beam, you can do beam C, or you can even do beam 4 or 3. And I said I'm going to show you how to deal with the staircase. So for now, assume there is no staircase, assume it is just a normal slab, and do the load distribution. But in a later video I'll explain how you should distribute your loads from your slabs. So having said that, I believe we have come to the end of our lesson today. So determine the loadings carried out by beam 2 and 3 and sketch all its loadings. So once before you go to the next class, kindly ensure you do this. This is your assignment, and come up with the loadings that you are going to use to design your beam. For design of this beam, we will design it manually, and we will design using softwares. We will start with using Procon. Procon is a design software that you can use to design individual beams. So we have done actually this design. It is in one of our videos. Find out our Procon playlist, and this exact beam we have analyzed and designed it for you using Procon. So thank you very much for you have been with us since the start of this. I believe you have learnt. Try finding this. There were small notable issues we noted with our work. For instance, when we were determining the height of our masonry, we used 2.4 instead of 2.55, and those ones were done intentionally so that you can we can note them out in this video so that you take care when you're doing your load takedowns. So go to Procon, design, do manual analysis, and then after that go to one of our videos. We have done this in Procon, study it, and it is going to help you even as you grow in your design journey. So thank you very much. May the good Lord bless and keep you for being with us. Bring your friends who want to learn structural analysis. Let them subscribe to the channel, and let us all learn together.